So everyone, welcome to another professional development seminar. Today's speaker is Srijan Agarwal from the Civil and Environmental Engineering Department at the University of Alaska Fairbanks. Dr. Agarwal received his PhD from the University of Minnesota, Twin Cities. His research interests include the fate of transport of oil spill response chemicals, water quality and treatment, environmental biofilms, drinking distribution systems, and urban air quality. He is the recipient of the prestigious National Science Foundation Career Award in 2018 for his work on microbial biofilms in drinking water, and was recently awarded an NSF Navigating the New Arctic grant to investigate the impact of climate change on Arctic water quality. Everyone, let's welcome Dr. Agarwal.
Thanks so much, Sebastian. Very excited and honored to present on this seminar at UAA, and presumably a lot of people here are attending from across different places right now in the times we are. So I'll start without further ado. So a little bit about myself before I start and dive into my research. As Sebastian said, my name is Srijan Agarwal. I got my bachelor's in civil engineering from India and in 2007, and then got my graduate degrees, master's and PhD at University of Minnesota, Minneapolis, Twin Cities. Then I did a short couple years stint as a postdoc also in Minnesota. And after that, I decided to find someplace a little bit more cold. So, and I found Alaska. So raised in New Delhi, born and raised in New Delhi, India. And it's a very warm place considered compared to, what you see in Alaska and most of the Midwest. And but then I got my education in IIT, that's Indian Institute of Technology, Delhi. And then I got my graduate degrees, as I said, from Minnesota. And that was the first time I ever saw snow in my life, because it doesn't snow in most parts of India. And then I did a postdoc stint in Minnesota at the Biotechnology Institute. And as I said, I found winter in Minnesota, and I found more winter in Fairbanks, Alaska. Temperatures in Minneapolis can also go pretty low. And but I should say in some ways it's an improvement, because it's not as windy as in the Midwest, and it's a drier winter here. So of course, Fairbanks also is one of the best places to look at the Northern Lights. And that's a picture from 2017, me and my wife looking at the Northern Lights like at 2 a.m. in the morning. But sometimes we get to see them like just right walking outside our house. Okay, what do I teach here? I teach a number of courses in environmental engineering. So undergraduate classes are Introduction to Environmental Engineering. That's a core course for environmental engineering majors. I teach an elective course in environmental engineering design. I also taught engineering mechanics courses. And for graduate or upper level courses, I've taught a course in air pollution management that I developed here. It was not being offered for a number of years before I started here in 2013. And then I taught a course in aquatic chemistry, which is a required course for a lot of the graduate students. And I've taught chemical and physical processes. And then last semester, I also taught the biological unit processes, which goes into the detailed aspects of wastewater treatment design. My research interests, they span biological, physical, chemical processes in environmental engineering. One of my major areas has been the role of biofilms in environmental systems. And this was my PhD topic. And you see here like a small disk with biofilms growing on it. And these are some reactors for biofilm testing in the lab. And then I also dabbled into a little bit of air quality modeling and measurements that had been sort of a side interest while I was doing my PhD. And then ended up teaching a course in that, and I have a couple of research projects looking at that. And then, of course, my general interests are also in water quality, contaminants, and treatment. The picture on the right is showing a burning oil spill, about which we'll talk about a little bit more today. So a little bit of highlight of some of my recent research projects. The first one is what Sebastian alluded to. It's about water quality in Alaskan communities, especially in the light of climate change, how it's impacting the water quality in communities as glaciers melt and permafrost thaws. There are expectations that a lot of carbon is being released, and that's ancient carbon and ancient microbiome. So some people say it is like waking up sleeping zombies. I don't know if it's as dramatic as that, but it's definitely, there are some engineering impacts it might have in terms of designing the treatment systems for a different kind of carbon load or a higher carbon load. So that just started a couple months back. And so we are very excited to start working on that. And then the other project that listed here is my NSF award on biofilm mechanical properties. This was my PhD research area, and I was glad to get continued funding to work on that more. And the third one here on the list is a food, energy, water project, which has a lot of actually people involved from UAA, including Jen Schmidt, Aaron Dotson, and other people. And so this is looking at a lot of different communities and how to use renewable energy for improving water and food security and even energy security in a lot of these small communities, which are called as microgrids. And that's why it's the term microfuse. And this image here at the bottom is actually related to my career grant. And this is a book chapter from our book chapter that we published last year. And this one is showing sort of the processes that happen inside a drinking water distribution pipeline with all the biofilms that are growing in there and what kind of processes happen there, the disinfection and the leaching pipes and whatnot. So it's I think it's a good representation, good way to sort of show people without actually digging out a pipe. And feel free to stop me at any point. I want to give a couple of slides about the biofilm, although the talk is not about biofilm, but I wanted to still introduce this because I think it's pretty interesting, and we all encounter biofilms in one way or the other. So what are biofilms? Biofilms are bacteria that settle on surfaces, and then they secrete these polymers, and they sort of form a house of bacteria, if you will, and that's called a biofilm. And so there's a surface, and there are cells, microbial cells. It could be bacterial cells, it could be fungal cells. And then there's this matrix, which is called the EPS matrix, or the extracellular polymeric matrix. And it's pretty interesting when you talk about biofilms, because bacteria, when they're outside the biofilm in the free-flowing bulk fluid, as you can see in this image, they behave very differently compared to when they enter the biofilm. And the bacteria in the biofilm are much more recalcitrant. They show a lot more, they're much harder to inactivate or kill. And so biofilm is a mechanism by which bacteria can protect themselves, but it's not completely understood yet what those different mechanisms are. It's not just diffusion limitation. There's all different kind of processes that happen in a biofilm. So much so that an antibiotic dose of, like, say, whatever is needed to kill a planktonic or a free-floating cell, you may need up to 1,000 times the dose to kill a cell inside the biofilm. And biofilms have been, found to be responsible for a lot of different diseases for which, you can't really cure them by taking simple antibiotics, including MRSA and a lot of other hospital-acquired diseases. So, and it's got a lot of implications in engineering, a lot of different impacts. I'll show an image here which very quickly summarizes. Like there are dental biofilms, there impact drinking water, which is my primary motivation of studying biofilms, oil recovery, cooling towers, ship hulls, food processing, medical implants. And this is showing dental biofilms. And so biofilms, we all encounter it every day. They're on our teeth, they're on the, if you go on a beach or a on the side of a river, you have a stone which is covered with an algal biofilm, slime, call it in a more layman terms. And these colors here in this image, this is the image from the Yellowstone National Park. And these colors are actually, they're owing to biofilms. And then this is a wastewater treatment trickling filter plant. And in trickling filters, we use biofilms to treat the waste. So in that sense, they're not all bad because they help us do a lot of good things, and they maintain the biogeochemical balance globally as well. So, and in the drinking water distribution systems, as an environmental engineer, where do we find these? So this is the source water, and then we have filtration. In the filter media, you have biofilms growing here. And it has been shown by a lot of recent research, that the biofilms that grow, or the bacteria that grow in the filter media, they impact the kind of microbiome or kind of microbes you see downstream. So it's a very emerging research area to understand what type of microbes live in our water. Our water, as you might know, is not completely sterile. It's not meant to be sterile. It has even any milliliter of water that you drink, even from tap water that is chlorinated, has millions of bacteria in it. They're harmless bacteria. In many cases, they're good bacteria. So people are trying to understand, can we control that microbial community in there? And what is it determined by? So a few studies have showed that these biofilms in the filters can impact the microbial community pretty significantly. And then when it's distributed, in the distribution pipelines, again, there are biofilms that can impact the water quality at the tap. Okay, so moving on to oil spills, today's topic. I'll present something about my research on herders for oil spill, but I just want to give a background on where I'm coming into this oil spill research from. When I started in 2013 at UAF, there was just a project that was getting started here at UAF, funded by the Arctic Response Technology, or it's also called the Arctic GIP. And this project was looking at applying a novel oil spill remediation method and testing that in Fairbanks, Alaska. So I got involved with that. I was really lucky, and to join the team with a couple of other faculty members and students, and then I worked with that team on a different topic. Always there's an opportunity in the faculty role to change gears, try different topics that you are excited by, and then working on that project. A few years down the line, on the right, the image is showing that I got a early career research fellowship from the National Academies based on my work on oil spills. So some of these funding have supported my oil spill work, which I'm going to be presenting today. Okay, talking about oil spills. So we all know oil spills are, everybody knows about the big disaster in 2010, the Deepwater Horizon oil spill, and numerous other oil spills. Alaska has been no strange. We are no stranger to oil spills. We have witnessed the Exxon Valdez oil spill much before the 2010 spill, and so there are multiple small spills that happen every week, every month. And if you go to the DEC, Alaska DEC website, they keep a log of different kinds of spills that happen on ground, on water spills. There are various spills of different sizes, very small to slightly bigger spills that happen. But with the warming Arctic and with the Northwest Passage being open larger duration of the year for passage of ships and potentially more oil exploration activity on the North Slope in the next few decades, as the Arctic is warming and providing more opportunity or window of opportunity to do that. There are expectations that there might be an Arctic oil spill of the magnitude of the 2010 or even much less than that, but still pretty significant. So are we prepared for dealing with those oil spills? So that has been sort of a national attention of preparing ourselves with technologies to deal with the potential Arctic oil spill. Now this picture here, this summarizes sort of 2 or 3 different mechanisms which are most common for dealing with oil spills. The one on the bottom third is skimming the oil, which is very obvious. Skimming is achieved with boats. You have these boats equipped with floating skimmers, and you skim the oil. It's also called mechanical collection many times. So you mechanically collect the oil and remove it from the water surface. And then one on the top here is dispersion, where chemical dispersion is achieved by applying these surfactant chemicals that you might have heard of called dispersants. And these dispersants, they remove the oil by breaking it into tiny droplets. And as you can see in this image, these tiny droplets then get dispersed and diffused throughout the water column and throughout the ocean. And they can then potentially be biodegraded by the inherent indigenous microbes in the water. And there have been a lot of work on that. There also have been concerns of the impact of addition of foreign entities, say the dispersants, on the marine aquatic environment. And the one in the middle is burning. It's also referred to as in-situ burning, meaning you burn it in place, and it's very obvious what it describes. You just burn the oil. So you can see here it says you need booms, which are long floating barriers to contain or prevent the spread of spilled oil. Now the challenge with burning the oil on water is that you need, as soon as you ignite the oil, suppose say there's an oil spill and the oil spreads out, and you try to ignite the oil, the ignition happens, but very quickly, the heat from the burn is quickly lost to the water beneath the burn, and the burning oil can get distinguished. So to avoid that to enable that continuous burning of the oil on the water surface, what is needed to have a minimum thickness of the oil. If the oil is, say, usually the figure is quoted from 2 to 3 millimeters thick. If the oil is 2 to 3 millimeters thick, it will continue to burn. So you have to apply to collect the oil mechanically, that booms, they are collecting them mechanically. And you might not know this fact, but there were about 400 in-situ burns during the Deepwater Horizon spill. So this is not something that's very new. It has been employed. But then how this might work for the Arctic, that is the question. So the need for herders. So I'll talk more about herders, but what herders are, they're basically another class of chemical surfactants. So dispersants are considered surfactants or surface active agents, and so are herders. But then they act in an opposite way as dispersants. Instead of dispersing the oil, they bring it together and coils the oil. And the spreading oil layer is thickened by the action of the herders. So they are typically applied on the boundary of the spilled oil and thicken the oil to make it more amenable to burning. So what is the need for herders? So these images are showing different technologies, mechanical recovery, booms and skimmers, in-situ burning, dispersants. So responders need access to all tools in the toolbox. In-situ burning is one of the 3 primary offshore response options. And as I said, you would usually need a lot of heavy booms to contain the oil, to thicken it. And this was The only offshore operational use of ISB was during the Deepwater Horizon incident. So it's not been used much before that. And herders can enable rapid ISB so that the attempt here is to try to thicken the oil without the use of these mechanical booms. Imagine if there is a spill in the Arctic with all the ice and everything, and the spill in the Gulf area, the Deepwater Horizon spill, it had a lot of the states, Texas, Louisiana, Florida, they have lots of logistical support there, a lot of personnel that could be immediately deployed. Temperatures not as harsh, of course, they're in much warmer temperatures than here in the Arctic. So there were those sort of things that were possible in the Gulf. But if an Arctic spill happens, logistically, it would be very challenging to do kind of these things that were done in the Gulf. So it would be very hard to bring all these booms in the ice-covered waters and so forth. And so while in-situ burning would be a very promising method to deal with spilled oil, how would you achieve that without deploying those heavy equipment and machinery and people in the Arctic? So that one answer is using the herders. These chemicals, if you can potentially spray them or apply them around the spilled oil, that could help collect that oil and make it amenable for burning. And if you can do that, aerially through a helicopter or through an aircraft, apply that herding agent, and then let the spill ignite, then that could be a very much simpler way to deal with that than deploying these mechanical booms. And here, the last bullet that mentions here, speed is the key to oil spill response. And the reason is that when the oil spill happens, the quicker you can attend to that, the easier it is to get more oil out of the water, because the more it stays into the ocean, the more it stays into the water, the more it gets mixed and the oil gets naturally dispersed, and that's called the phenomena like weathering. So the weathered oil is much harder to deal with than fresh oil. So herder technology description. So herder uses a surfactant boom, as I said, to thicken slicks. There's no boundary required. Herders typically require at least an order of magnitude less product than treating slicks with dispersants. And this technology was originally developed for open waters. And in 2000, the research focused on marine applications with ice, but more recent research has again concentrated on open water. The goal is to develop another tool that can be readily applied to make ISB a routinely used response option. So there's been a lot of this research into in-situ burning, because this is one method which can remove more than 90% of the oil from water very quickly. And as you can see, these images here on the top, it's showing a mechanical boom which is collecting the oil, and the one here showing a surfactant boom. So sometimes the herders are known by different names: chemical herders, chemical surfactants, or in this figure it said surface collecting agents. So surface collecting agents are sprayed in water around the perimeter of a slick, and these surface collecting agents rapidly spread to form a monolayer of surfactant on water surface. And these surface collecting agents, or herders, they change surface tension of water, forcing the slick into a smaller area. And yeah, and then it's more amenable to burning. So here you can see in the middle is the thick burnable oil, and the herding surfactants that align at the water surface typically. So they don't dissolve completely in the water, they stay at the surface, these surfactants. Now, how are herders used? Herders are used as a means of controlling a slick to improve performance of other techniques and as a precursor to in-situ burning. And herders are used to thicken a slick greater than 3 millimeters so that it may be ignited. and it's effective without the need for extra containment equipment. So here are some videos from our collaborator on the project, the GIP project. The collaborator on the GIP project was a consulting company out of Canada, SL Ross. And SL Ross has been actually one of the key players in developing this technology for oil spills in the past couple of decades. So that project was in partnership with SL Ross. And there are a couple of videos from SL Ross. And let me see if they will play. Hopefully they will. Yep. So you see here, I'll pause the video. There's an oil that is spilled in a testing cell. And so it spreads out immediately as it would on a water surface. And then you would go around and apply a very tiny amount of, you use like microliters or even milliliters of herder or the herding agent. And as soon as you, and this video is like a little bit time, I just shortened the video for it. It takes a little bit more time to do that, but as you see, I'll show that again. As soon as the herding agent is applied, very quickly, within seconds, the spill contracts and becomes thick. Okay, this is another video now. So this one is which has a lot more. This video is having presence of ice, and you can see it's not as uniform, the contraction, as it was in the previous video because of the ice. So let me show that again. So there's all this ice, and you can see sort of these patchy spread of oil, and then it contracts with the herder. So that's basically how the herders behave. And so this is just showing some other videos about testing. This is again spilled oil, and then you let it spill, let it come to equilibrium. And after it comes to equilibrium, you would go around and apply herder. And as soon as you apply the herder, the spill becomes immediately contracted. And based on that, this is a confined testing scenario, the spill can hit the walls and so forth. And here again, you see the spread of oil, and again, you see that contraction of oil. And this happened just at the surface. And there you see this interesting phenomenon. Now the spill is breaking into two. So sometimes it can break into 2 or 3 parts. And the less you have of that is better, because you lose your burn efficiency. You lose the amount of oil you can remove from the water surface. So use of herders in Arctic waters. As I said, you would want to use herders in the Arctic to aid in-situ burning, because Arctic has its own unique characteristics that make in-situ burning favorable. And because of the logistical and technical challenges, you need different kind of methodologies. So this figure from our paper, 2017 paper in Cold Region Science and Technology, which summarized the field experiment we conducted in 2015. So it is showing the same thing. You have the oil spill in the presence of ice. You have a helicopter that is applying herder to contract the slick. So you apply herder aerially and you contract the slick, and then the contracted slick is ignited Now, again, from a helicopter, you can use something called a heli-torch, which basically can ignite aerially the contracted slick, and then you can have greater than 90% oil removal. Now, there are different scenarios for herder use. I won't go into a lot of detail, but there are like, if you look on the left side here, the different approaches are mechanical recovery with no ice management, mechanical recovery with ice management, or in-situ burning, and the different ice covers and different wind speeds. And you can see that in-situ burning is favorable in a lot more scenarios than the other techniques. So for the aerial application of herders, we did a field test in 2015 in the Poker Flat region of UAF, which is about 30 miles northeast of Fairbanks. On the Steeds Highway, there's a university-owned property, which is usually used for launching rockets and such. So at that location, it is far from major population center of Fairbanks. We constructed a 90 meter by 90 meter pool, if you will. It was not a very deep, it was like a feet deep pool, and filled it with 6 inches of water, 90 meter by 90 meter, and spilled a barrel of oil. So the crude oil was released using a spill release frame. The oil spread towards equilibrium. Herding agent was aerially applied around the spill. The oil spill thickened under herder action. The helicopter lands, and then it loads a heli torch and unloads the applicator. The thickened oil slick was aerially ignited by discharging gelled fuel on the oil, which is using the heli torch, and in-situ burning of oil was initiated. And then in conjunction with that test, so this one is a field scale test, we conducted a few more tests. We conducted some lab scale tests. So we wanted to see the effect of scale on the testing of in-situ burning, because you can't always do a field test. That field test was very involved, and we did like 5 tests over a week, but it required like a whole year's worth of preparation, a huge team. Lots of people on site, from Alaska Clean Seas to the all kind of safety people on scene, and fire responders, and yeah, so we have every kind of, we had a 300-page safety plan that was prepared 6 months ahead of time. We had a lot of arrangements for the field test, and that was important to, to look at the feasibility of some of these things on a larger scale. But for understanding more like more detailed aspects of the phenomenon, you would want to do maybe smaller scale laboratory tests, lab tests, or meso-scale tests, as we call it here. So we did 3 experimental scales, a bench scale test, and a meso-scale test, and a field scale test. So when we use the fresh, unweathered ANS crude oil, and there are a couple of different herders that are available right now, and there's actually a lot of research going on to develop, better and more efficient and more biodegradable herders. But we use a product that's widely accepted, Siltec OP40. That's a trade name, so it's a kind of a not very intuitive OP40. It's a trade name. It's made out of silicone mechanicals, and we use partial 10% ice cover in fresh water. And ambient temperatures, it was April 2015, March to April timeframe, and the temperatures were below freezing. And you can see the images here. So that's our bench scale test. We made a small bench scale cell, which could do a lot of different things. And we did a number of tests using this pan scale test. And then we had meso scale test at the local fire station, and we had the personnel on site, and this was bigger than this, but still much smaller. And then of course we had the field scale, where we had like 90 by 90 meter, and we made some artificial ice there, And of course, by the time we had to do the experiment, some of that ice melted, and we put in some faults like metal pieces to simulate the ice at that scale. All that information is in our publication and referenced on the bottom. So you can see this is the impact of herder application. This is prior to herder application. You can see all this. It's hard to see sometimes because, but if you can see carefully this, you can see the black oil and this crude oil. And then after herder application, it's contracted. It's easier to see in the bend scale, but meso-scale, because of the reflection of light and the black liner that is being used, it's hard to see exactly. But in the field scale test, you can see the oil was contracted, and these are sort of the false or imitation ice cover. So this is the ignition of burn after herder application in the meso-scale test. And this is in the field scale test. This is the helicopter and the heli torch. And there are a lot of videos we have. I didn't include them here in this presentation, but there are a lot of videos for this experiment. And then there's something we calculate called burn efficiency. Burn efficiency is the percentage of mass removed, basically. So that's the mass of oil released minus net residual mass divided by the mass of oil which was released. And it's an indicator of the amount of oil that is removed after in-situ burning. We saw in our experiments that burn efficiency increased with increasing scale of the experiment. So for our bend scale studies, we had like about close to 40% burn efficiency. For the meso-scale, it increased to slightly greater than 60%. And for the field scale, it was an average of 80, but as high as 95%. And so the larger burn, we were wondering, like, why do we see that? Why is there more oil removal for larger scale tests? So larger scale, larger burn produces more energy, which creates strong convective currents aided by a rising mass of hot air within the burn, which is sometimes called as a stack effect or chimney effect. And this is not something that just we have seen, but others have seen that also, these kind of phenomena. But we, because of using different scales, we saw that pretty starkly. Because you can imagine that if you have a larger burn, and so that's the larger the burn, it's sort of it has the self-herding, as some people say, a self-herding potential that herds the oil. It sort of pulls in more and more oil into the burn and takes it to more higher burn efficiency. In smaller scale burns, you don't see that phenomenon. So that is one hypothesis that others have proposed, and we propose as well for this kind of an observation. But that was interesting to note that. So these convective currents can cause natural contraction, internal herding, leading to a higher burn efficiency. Letting the burn continue to completion helps achieve higher burn efficiency. Breaking of slick into multiple sub-slicks would lower the burn efficiency. So these are some of the things that we saw from our experiments. Weathering of spilled oil can reduce burn efficiency, and higher fraction of lightweight volatile compounds in oil and lower water content in the oil both tend to increase the burn efficiency. So if you have more lightweight and volatile compounds, they're more readily combustible, and they will burn faster than if you have really heavy oil. The percentage of ice cover can both increase and decrease burn efficiency depending on the slick thickness and the water content. If you have like a greater than 50% ice cover, sometimes that itself acts as like a more and that ice doesn't allow the oil to spread out too much. So that way it could increase burn efficiency. But if the ice sort of helps in breaking the slick into multiple sub-slicks, then that would reduce your burn efficiency. So we also looked at herder application rates. As I said, the herder application rates are much lower, usually a factor of 10, as compared to the dispersant application rates, because very intuitively, the herder is just applied on the boundary of the slick, On the other hand, for the dispersant, it has to be applied in the whole slick. And the recommended harder application rates are very low, 5 to 15 liters per kilometer or 50 to 150 milligrams per meter squared. And so you can look at this table here from our paper. We did bench scale studies, 6 experiments, and which used 50 milliliters of crude oil as a spill, and then 0.515 ml of the OP40 herder. And there's an estimated herder application rates. And in one of the experiments, we used a much higher application rate than the others. And so for the herder application rates, we saw it's easier to control herder application rates in bench and meso tests, which is also understandable. Precisely targeting herder application rate is challenging when done aerially. So you have this huge helicopter, like in this tiny little, area where there's oil spills. So for the operator, the pilot, to sort of be able to, with a dangling mechanism, to be able to directly apply the herding agent around the slick was challenging. But then we also saw that, we had like 5 experiments, the field scale experiments, with each experiment with each day, and with the same pilot, we had a much better handle on how to do that. So that's, points to the operator training, importance of that. And bench scale experiments revealed that it was difficult to ignite and sustain a burn when excess herder was applied. So what does that mean? So in the previous slide, I showed that in one of those experiments, we had excess herder application. So there has been like, some people ask the question, what if you apply more herder? Is it good or bad? So that's what we wanted to test. And we didn't do a lot of experiments, but those limited experiments that we did, we saw that it was difficult to sustain or ignite the burn with excess herder. So there's something to say about not applying more than what you should, operationally speaking. Now, there's another aspect of management of burn residues. So you have these like heavier fraction of burnt mass of the oil that's remaining on the surface in the bench scale, meso scale, and field scale. In all the experiments, we saw those residues. And so in general, the residue of unweathered ANS crude oil floated and it could be recovered. The previous studies have shown that highly weathered and emulsified oil from the deep water horizon, that generally sank. So it depends on the different scenarios and different other factors, whether the residue will sink or float. And the decisions are made, the residue management decisions are made on a case-by-case basis, considering the net environmental benefit. Is it more efficient use of time to go collect the small amount of burn residue, or do more in-situ burns and remove more oil from the surface? So for example, in the Deepwater Horizon response, the US Coast Guard decided that it was better to spend resources elsewhere than trying to collect a small amount of burn residue. That, so weighing those different options to invest resources in that critical time, that was a sort of a decision that responders need to make at the site. So the residue was left to settle into the water column and to the seafloor. So I know we are at 12:30, and I'll be finishing shortly in another couple of minutes. So we did some more studies looking at the herder monitoring in their field site. So surface tension is one parameter that is like a proxy for the herder concentration in water. It's, looking at it from a surface chemistry point of view, we are reducing surface tension as you apply these herding agents. So in this, on the left plot, you see that in this window during the field test, our surface tension dropped dramatically. And then soon after the field test, it starts to come back up and up and up and up. So, and then we also did like OP40 measurement, measuring it using the GC's mass spec. And then these shows like, very quickly within like almost like 2 to 3 weeks after the test, the concentration of the OP40 was almost back to the background non-detect levels. So this is, I mean, we were just doing like, we didn't do any more like exploration or investigation of why that is happening. Is it like photo degradation? So this was like a very open area, and this was, as you can see, the time frame here, April to June, July. We get a lot of sun at that time in Fairbanks, and this is, in a very open area. Is it because of the temperatures? Is it volatilizing? Is it just photo degrading? Is it microbially degrading? So what exactly is the mechanism by which it is being lost is still an open question, and it's worth researching. And there are, I know, like as I mentioned, some other people in UAA and other places are looking at, and UAF are looking at some of these things. So you might see in a lot of these citations here, Bullock et al. So Robin Bullock, I have her picture at the end. Robin Bullock is a PhD student who's been working on this project and this topic with me and other faculty members since 2014. And she recently published a review article that we published in Science and the Total Environment. And this is a summary figure that we prepared for the review article, which shows the burn efficiency from like a lot of different in-situ burn studies. And there are, on the x-axis, there are different kinds of oils. Macondo oil, which was the one in the Gulf that was spelled, the Alberta sweet oil, and ANS crude is Alaska North Slope oil here, and lots of different oils across the globe. And you can see that the burn efficiency is pretty high. It can be more than 80%, and some of these are a little bit lower. So yeah, more details in our in the review paper. But in general, burn efficiency from in-situ burn has a potential to be very, very efficient as a process. And this one is showing maximum oil slick thickness after the further application from the same review paper. So you see there are two main herders, the thick slick and the OP40 right now, and there are some others, Corexit and the EC9580, that are reported in the literature. And so you can see, looking at this, looks like OP40 is much more effective at thickening the spill than the thick slick. But on the other hand, the thick slick is, previously it was named as a US Navy herder. Now it's known as thick slick as a trade name. It's a more hydrocarbon-based herder, and is more biodegradable. And so more focus is being spent right now on the thick slick than OP40, which is a silicone herder, and apparently not as biodegradable than like thick slick. But it's more effective at lower temperatures and in most scenarios. So, but anyway, these are just four, and as I said, there's a lot more research being done right now to make plant-derived and naturally biodegradable surface active agents, which can do similar things as OP40 and thick slick. So that's it pretty much. These are some of the references, and this is an amazing team. And I acknowledge the International Association of Oil and Gas Producers, Arctic Response Technology Joint Industry Program. Then we got some funding from UAF, the State of Alaska Hydrocarbon Optimization Grant, personnel from SL Ross, Ian Gust, Steve Potter, David Cooper, Alaska Clean Seas, UAF Fire Department, Bill Shraji, and the UF team pictured below, Jessica Garan, she was the lead in a lot of the preparations for the field experiment. Robin Bullock, the PhD student, she's supposed to be defending sometime this year. She is currently an adjunct professor at Colorado School of Mines, and we're super proud of her. Bill Schnabel, who was the PI on the UF project, the JIP, and he's currently the Dean of Engineering at UF. Bob Perkins, he was till recently he was the department chair of civil engineering, but he works in environmental risk management and toxicology. Robin Bullock is a co-advised PhD student with Bob Perkins and myself. And then the last one pictured here is Patrick Sarts. Patrick Sarts was a master's student who did some of the work on air quality impacts of in-situ burning, which is a different presentation in itself, but we did a lot of work looking at the emissions from these burns. So with that, I will stop and see if there are any questions. And thank you for everybody's attention.
Oh, thank you very much. So yes, we do have a question, and I think you actually have a slide that may help address it. It is, what % of the oil can be burned with the contracted but highly divided spill in icy water versus open water?
Yeah, and I think it's dependent on a lot of different things. What is the weathered state of oil? If it's a divided slick, the burn efficiency definitely goes down compared to if it's not a divided slick. And the state of the oil, if it's weathered or not weathered, and so yeah, I don't think there's a number. And also you see, like, let me go back to one slide here. With different oil under different conditions, it can all, it's much variable, but in general, you can say that a divided slick would have a lower burn efficiency.
And it looks like the minimum there is about 30%, is that right?
Yeah, on an average, it looks like, I mean, the minimum here is even like 20%, but, you'd have to go back and look at those papers, which are referenced
Oh, I
in this
see.
and see what caused that. So it can range, but for most studies, it's, in-situ burning in general has shown greater than 60% burn efficiency. But then again, yeah, a lot of different factors at play that you will need to look at. And actually, I was invited by earlier this spring, by the Coast Guard in Louisiana as a part of a presentation they were giving to first responders on the topic of herding agents. It's a very emerging topic, and people are still trying to understand what this all means for the different scenarios. So I think the knowledge on this whole topic is very much in an evolving state.
Awesome. So we do have a couple more questions. One of the other questions that we have is, what is the thickness in millimeter of oil, of the oil slick on the water surface necessary for it in situ burning to work?
Yeah, that's a pretty common question. And if you look at all the papers, it is about, and it's the exact number is slightly different in different papers. And that's, again, potentially because of the different kind of oils. But typically the number is about 2 to 3 millimeters. You need at least 2 to 3 millimeters, or to be on the safe side, if you have more than 3 millimeters, that's target range for a lot of different scenarios.
Yeah, and the herding agents then, may make that feasible, where, you might have less than that. You add the agent, right, the herding agent,
Exactly.
and then that'll actually gather it up and make it an actual thickness that you can work with for in situ burning, correct?
Right, correct. Yes, that's correct, Andrew.
All right, I believe that is all the questions that we have. Thank you so much.
Sebastian.
I had just one quick question. I was kind of curious about the non-circular shape of the herders. You said that sometimes when ice was involved, it looked like it wasn't one big sort of blob that came together. And so how does that sort of affect the efficiency? I think you kind of addressed it, but I'm just curious, like what effect did that have on the efficiency, and when do you see a lot of that non-circular sort of effects?
I guess it's in the non-circular, mainly when you have obstacles. And actually, it's good that you brought that up. So right now, I am actually working with a collaborator from University of Southern Florida, and he's a fluid mechanical engineering professor. And what they're doing in their lab is they have a lot of good photo capture techniques, advanced photo capture techniques in their lab. And they're setting up these, what they're calling it as racetrack experiments, where basically they're putting these different shapes, some circular shapes, or cuboidal shapes, for oil spill, a simulated oil spill, and then trying to observe that the impact of these these different shaped obstacles on the division of the spill, and how that might impact the herder efficiency and contraction of the oil, or how much of the oil can go from one part of the tank to the next part of the tank. And so basically trying to understand the impact of these, you can call it obstacles or ices in this case, or ice in this case, that might have on herding. So yeah, again, as I said, a lot of cool work going on a lot of these aspects of this. And there's a PhD student, I'm on his committee as an external committee member, but that's what they're looking at, different shaped obstacles or ice flows, than what kind of impact they would have. But in general, whenever you have that weird shaped, contraction, we see lower burn efficiency, primarily because that chimney effect is lost, and also, if the spills divide, then, again, that similar impact is observed.
Oh, interesting. Well, I think that's all of the questions. So I just want to thank our speaker again. So thank you, Srijan, for the presentation and your time. And thank you, everyone.
Yeah, thanks so much, Sebastian, for inviting me, and hope to see you in person sometime.
Yeah, it's nice talking. Bye.
Bye.
Okay.